Okay, now in this slide and in the next slide I will explain this direct map cache first, and this is our virtual memory, and let's assume that PC start from the offset 000, and in our direct map instruction cache here, let's assume that the cache is empty. Okay, that means the valid bit are all 0. Okay, they are all 0 like this. Okay, now let's start with subfigure A. Subfigure A is the beginning, and then we will continue to subfigure B and C and D and so on. Alright, are you ready? Let's go. So PC start with this 00 offset. That means the CPU will try to look for this cache location. Okay, because this cache location correspond to the virtual address offset 000, okay, which contains nothing or junk, because the valid bit is 0. Okay, that means this is a miss in the cache. So the CPU, the cache controller will read this instruction and put it in here and modify the valid bit to be 1, just like the next figure, subfigure B. Okay, so when the cache contains this instruction, that means the CPU can decode and execute this instruction. Okay, therefore now PC is PC plus 4, which is this offset 004, and this 004 correspond to this cache location, which again its valid bit is 0. That means it caused another miss. Therefore the cache controller will copy this instruction and put it in here and modify the valid bit to be 1. Okay, and that correspond to this subfigure C, and that means the instruction can be decoded and executed already. Now the next PC will be 008, because PC will always be PC plus 4. Okay, which means from 004 the next instruction the next location on the next address will be plus 4 like this to be 008. Now again, this location 008 correspond to this cache location, and of course, as I mentioned earlier, the valid bit is 0 because we assume that the cache is empty at the beginning, so it caused another miss. Okay, and the instruction will be copied here, and the valid bit will become 1. Okay, then as you can see here in subfigure D, the instruction is already copied and decoded and executed. Now according to the label adder, it corresponds to 030. That means PC now becomes 030, and 030 correspond to which location in the cache? This number correspond to this cache location. Okay, so this cache location again is empty because the valid bit is 0, and then it caused another miss. Okay, and this instruction will be copied here, and the valid bit will become 1. So let's continue to the next subfigure E. As you can see, the instruction is copied to the cache, and valid bit has been 1, has been modified to 1. So the add R0, R1, R2 can be decoded and executed as usual, and the next instruction will be PC equal to PC plus 4, which is 034, okay, which correspond to BXLR instruction, but it's not available in the cache because 034 correspond to this cache location, which is still invalid, so it causes another miss. Okay, therefore this instruction will be copied and the valid bit will be modified to 1. Now let's continue to subfigure F. So the instruction is copied and decoded and executed. Now the next PC should be returning to the LR content, LR address. Okay, so LR save this number here to be 004. Therefore PC will be 003. PC will be 00C. Okay, so 00C correspond to which cache location? I see here 00C here. Okay, so this is still invalid, right? So it caused another miss again. So therefore this CMP R0 will be copied here, and the valid bit will become 1, and we will continue in the subfigure G like this. So CMP has been copied and decoded and executed. Okay, now PC will become PC plus 4, which is 00C plus 4 is 010. Okay, now PC points to this address number, which is BLT loop, but this 010 correspond to what? 010 correspond to 010 here in the cache, and as you can see, they are not the same because we are human, but in hardware this is already valid. Okay, but the tag is different from this tag. Okay, therefore it caused another miss. Even though the valid bit is 1, but the tags are different, it causes another miss. Therefore BLT loop will be copied to replace this instruction. Okay, and we continue in the subfigure H. As we can see, the BLT loop is already in the cache and decoded and executed, and it depends on the result of the comparison. If the comparison is true, that means that means what? That means the PC will jump to this location again, right? 0 1 0 0 0 here, and this location can be found in the cache already. See that 0 0, it corresponds to this location in the cache, and it can be found because the tag of these two are the same. Okay, so if the result is true, that means the cache will hit again, right? The cache will hit, and this will save a lot of time to fetch the instruction to the CPU. Okay, therefore we don't need to fetch the instruction from memory, we fetch the instruction from the cache directly, so it saves some time. Alright, and this is the purpose of having caches. Okay.